Hey, okay, let's work into more practical applications. So we're moving away from the straight pipe or probably a cylinder. So here now we have an elbow, it's a 2D. So we are going to, in this case, all geometry, everything meshing. So see also the mesh. Now we're not using any more triangles, squares, but it doesn't matter. So we're going to have an inlet, outlet, another inlet here. So we have water entering different temperatures. So something like that we're going to get. So let me plot temperature field. So look at your temperature field, velocity field. So we're going to work in this case, okay? So let me close here to do everything from scratch, okay? So here we have the dimensions. You can download it from the course website. Okay, so we have everything in millimeters. Okay, so let's do this geometry. Okay, it's relatively easy one, but let's do everything from scratch. So remember, so look at what I'm doing here. Here I'm adding the whole workflow. So we have I have two workflows, original one and another one. I modify it. I added few more things. So to use this workflow, you just put it here, okay? And now I will work in this one. I will use Design Modeler to create the geometry. We have the dimensions here, okay? So it is in millimeters. And let's wait while it opens the Design Modeler. Okay, we are inside the Design Modeler, so I hope you remember, but first, so this is a 2D, so we only need to do the sketch and then convert it to a surface. So I want to sketch here. We create my new sketch, put it normal to the screen, and now let's go and do our sketch. And before sketching, also I would like to use this option, snap to grid, and show me the grid. So we have a grid there. So let me draw first. We have a rectangle. Let me put it here in the origin. And I just draw some lines. Okay, and now I can give dimensions. So I use general. Okay, you can use also horizontal. It's not a problem. You have your dimension there. So this one will be okay. So to show you something else as well, the conversion, scaling, and Fluent. So let's put this one 2. Okay, or not 2, let's put 20. Okay, and this one will be 10. Okay, good eye. So let's keep drawing. So see that it's quite easy. We have all the reference dimensions here. Okay, so let's create the other rectangle. Okay, so let me also hide at this point the grid that is cannot see well. Okay, but I still have the snapping. Okay, so I will draw in another rectangle. Okay, so boom boom, we have it there, and now again we give dimensions. Okay, so we have here will be 100. So general horizontal from here to here. H3 is 10. Okay, then we have a vertical from here to here. 10. Okay, and now we have a construction point, so we can go here. So let me put should be that one. Okay, we need to give dimensions there as well. So we'll give vertical here to here. Okay, 10. And the other one is already there, but it's the one you can check it. Okay, here, here. So it's over constrained. You need to put it. Okay, so you can erase it. Here, delete. Okay, so we have these dimensions. Now we can draw a circle. So if we go back to geometry, see that we have this arc here, another arc here, and then we add the small pipe. So, by the way, I'm creating in this way. Probably this is not the best way to do it. There are many ways to create a geometry, okay? So I'm just using this one, drawing lines kind of in a random way. So let me give this one also should be 10. This one also should be 20. Okay, so we have it there. And now I can go draw so you have all your entities here. So as you can see, it's not the best parametric CAD software, but it does good work for relative easy geometries. And then we have the second one there. Okay, so now we need to erase this part of this circle. So there is modify, and see that you have many options to modify. So we want to use here trim. So see that it will trim, another trim, trim, another trim, and here. And we have now the pipe. I don't need this here, and I don't need this one here either. Okay, now what else? Okay, let's go dimensions, modify, move. Let me move. Okay, so we have all this. We do some dimensions. There is not a problem. So now we need to create the other small pipe. Okay, so let's do something. I will create it in 2 steps. So we have this first one. Okay, so I can go here and have that one. So you go concept. Remember, surfaces from a sketch. You select your sketch, apply. I like to use always here at frozen, generate, and we have the first surface. Okay. Now let's create a new one. Again, same. We can, I think, if I create, okay, here I will create another sketch, and now I enter here. Okay. So now that I'm here, I can go and draw that small pipe there. So now we can give dimensions in reference to the other. So I have the bottom from the top is 20 to 5. So I can go dimensions, vertical, from here to here will be 20.5. Okay, 22.5. And then I need, okay, we have, okay, it will be 2.5, okay. So now I can give this one. .5, okay. So if I say 2.5, and now I need to define another one from here to here. Okay, so if I create this one, I have the dimension there, so it will be 1375. Okay, let me go 1375. Okay, so I go here, will be 12.5 if I'm not mistaken. That is, yes, 12.5. Okay, so we have the pipe. Okay, we go back here and surface from sketches, we create the second one. Okay, so here at frozen, generate, and see that we have 2 surfaces. So now what we need to do, we need to create a single surface. Remember, you have 2 bodies here, and to do the dimension we need a single one. So, oh, I think I'm missing, no, I'm not missing anything. Okay, it's okay. I thought I was missing a dimension. Now we need to merge. So we have booleans here. So you see that you have many operators. So boolean, we can do merge. So UNIGE, select 2, control, and select the second one, apply, and now generate, and see that we have a single surface there. Okay, so it's this one. Probably you see these lines, remember, represent the sketch, so you can hide that sketch. So as you hide the sketches, you see now clearly that you have a single surface. So now that we're here, so also you can do here, go fluid, not computer, but I like to do it. I will call it domain. Every now and then, remember to save. So now we have a geometry, okay? As you see, quite easy. We close. Okay, we have this one, and now we can go here, click here, and we go to meshing. So it will import automatically geometry here, and let's do the meshing. So let's wait while it's open. Okay, we're back. We have our geometry. So remember, always here in mesh, be sure that you have your CFD. In the physics, you have CFD, you have default parameters, and you can always press generate, and let's see what of ANSYS measure proposed. So this is okay, but it's a super quad measure. So remember, we need to select method, now add size and functions, inflation layer, name it selections, and we're done. So let's do it. We'll do it here. Method, so select your surface, applies. Here you can select a method. Okay, you have this action, so we'll choose quadrilateral dominant and then all quad. Let's see, generate. We should have something similar. Okay, so now let me add okay, all quad. Okay, didn't manage to create all quads, but doesn't matter. Insert now a sizing function. I will add a sizing in the whole domain, and here you can choose this size. So let's see that I want something about 0.5. Okay, yeah, that seems about right. Press. So remember that, just know the size. You have that circle there. You see this, well, I have a problem with it. You see the circle there next to the cursor. That one is telling you the reference dimension. So we have that. This is very nice. Okay. So now what else we can do? We can add also some refinement here. So remember from the cylinder case that we can create bodies of influence. In this case, we don't have one, but we can play with the lines, the edges to add the refinement there. So I can go insert, sizing, select here the edge, this one, and this one. Okay, with control, select multiples, and now you can add there a different refinement. So see that 0.1, it will put this here. You have your visual reference, and also change this value. Remember, this is the growth rate, so how fast it will grow from here to the internal volume. So if you leave 1.2, probably you will have larger cells in the center. So if you put a small one, it will be all uniform. It will grow all uniform. So now we're done here. Generate. And voila, we have this. But notice here, or here you see that you have this growth rate. But okay, let's ignore that. Okay, this is okay. So now what we're missing the boundary layer. So that is what we need to add now. So you go insert, and you have somewhere here inflation. You select the volume, and then we do selections on the edges. Okay, so you go here, 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 here. Okay, here. Here, and here. Okay, you go and now apply. You select those, and this is proposing a default value of 2. That is not too much, so I like to use 8 and generate. Okay, as you see, we have this. This is quite nice mesh. Okay, so you see they resolved very well. So here you will have some large skewness. Okay, so you know, skewness is this deviation from the cell center to the face center. But Fluent does a very good job, okay, to reduce those errors. That is not a big problem. So remember, you can also play around with the different parameters. So here we use a smooth transition. I don't recall the law that it used for this one. You can go to the documentation. Always remember that you have the help, somewhere you have help. So it's very good. But in any case, you have here different total thickness, first layer thickness, so you can compute a priori your normal distance from the wall to the cell center using your target y plus. But I will use here a smooth transition, so we're almost done. Now we need to add name selection. So select that one, create name selection. That will be inlet 1. I will go here, and this one will be that will be okay here, inlet 2, and then we have the outlet. Okay, so select here, name selection, and outlet. Okay, so we have all our name selection. I didn't put it for the walls because by default is you don't give anything. Fluent will group everything with the default name, and you can select it as a wall. Afterwards you want, you can do it. So we're done here. Okay, so also, well, so you want to know the number of cells that you have here, go here, statistic, and you have the number of cells. Remember, everything is parametric. So for instance, if at this point I would like to use triangles, you go there, change to triangles, and everything will be updated automatically. So now you have triangles. So it's up to you to choose quads or triangles. So I will use quads, so I will go back here, quadrilateral dominant, and let's get the quad mesh. Okay, so we have this, we have our name selections, and we're ready to go. So now remember, right click all the time when you have the light in there, you need to update it. So in this case, it is converting the mesh from ANSYS measure format to Fluent format, and then we can enter to Fluent. Okay, so we have the mesh, it was converted. So I won't go here into you press here, double click, you will enter into Fluent. I will go already, I open this case that I have the predefined setup. Okay, so this is the mesh I have. Okay, nice mesh. Okay, probably was different to the one that we generated previously. It's up to you. Case one, keep that one, or you open the tutorial, you can download it. It's up to you, doesn't matter. So let's go through this setup. Okay, so remember, when you are opening, remember to select double precision. Okay, it's always important that one, so the double precision. And in this case I'm running one processor serial, but if you want to go parallel, it's up to you. So we go into general, always this vertical approach. So I will use pressure based steady, so where we are going to have the opportunity to play a little bit with the under-relaxation factors, with a more realistic case. Then in models, enable energy. Okay, so we want to add temperature, so we need energy. Go viscous, your turbulence model, so choose any model you want. In this case I will use K omega SST, but feel free to select any model. Remember, less this scale resolving requires transient stay in the runs, nothing else here. Then go to materials, and let's add water. Okay, so you go materials, choose create, and then you can add a new material. So look Fluent database, look for water, it is in the bottom, and choose liquid water. Okay, so for instance, you select one, just copy, and you will have that new material available. Okay, so now that you have the material, okay, remember, the solid doesn't matter, or the solids you are doing conjugate heat transfer or fluid structure interaction, you have those options here. If we are not doing that, so we don't need to define anything. So you go into Sun, okay, enter there, and here you need to select your material. So here by default will be air, choose water or whatever you want to use, but let's use water, and okay, you are there ready to go. So then we go boundary conditions, and you will have this boundary conditions. So remember, I told you that whatever you don't add a named selection, Fluent automatically will create this wall surface underscore body or whatever the name of your domain. So see that inlet is a velocity inlet. Okay, so we have a velocity inlet and put this value 0.4, okay, normal to the boundary, and then intensity at the inlet will be 5, and then the hydraulic diameter 0.1 in this case. And now I remember I forgot something to mention. So you need to scale your case. So look at that. By default, okay, I think it was, okay, let me scale. So let me show you how to do the scale. So it was 100 and 100, okay. So I think, okay, right click here, we should have dimensions. So you go here, scale, and you have the dimensions of your domain. This is very important because sometimes you take some geometries in inches or millimeters, okay, so you will need to scale everything, okay, to your actual geometries. So you should have probably something like this, if I'm not mistaken. So we need to scale it to 0.4. So here you will select, you have convert from units, or you give the scaling factor. In our case, I will put 0.1, 0.01, 0.1. In your case, I think it will be 0.1 because it will be 0.1. Yeah, but in any case, you get the idea. So it should extend from 0, 0.4, 0, minus 0.025, 0.4. So I have this one because when I was creating the geometry, remember that I tried to put this vertex, I put this vertex in the origin, which is coordinate 0, 0, 0. So you put it somewhere else, you will have something else, but the extension should be 0.4. Okay, so we're here, you go inlet, so see that velocity, 5% intensity, and your hydraulic diameter, you give it here. You have your small program, so if you want to compute k omega, you can put it there, so it's up to you. I like to use this one, there's no problem. Then you have inlet 2. Inlet 2, we're going to give this value, so you have 1.2, so see that we have a larger velocity here. Always remember normal to the boundary, or you can give the components. Then again, intensity and hydraulic diameter, 5, your turbulent intensity, and then you give the diameter of the pipe there. The outlet will be a normal outlet, okay. So here I'm putting these values, okay. So probably would be better if I put here again intensity, hydraulic diameter, and let me put 0.1, okay. So these are velocity values, but remember that we have also temperature, okay. So as you go here, you will see that now you have this thermal tab enabled, and you can give the temperature. In my case, I'm working in Celsius. By default, Fluent works in Kelvin. So if you want to change the units, you go here and see this tab, units. And you go here, look for the quantity, and you select, for instance, temperature, and default will be Kelvin. And you see that you will have it in Kelvin. So let's work in Celsius here, showing you more actions, select, and you put 20, inlet, and see, also always pay attention to the tabs, okay. If you have some tab here available, it means that you need to give boundary conditions. You go to inlet 2 and see that you have thermal again, and let's say that here the water enters at 40 degrees, and you go to outlet, and remember this is about flow, okay. In the case that it's coming back, it will use this value, so kind of would be an average between inlet and outlet, okay. So if you want to put 30 there, put 30, it's up to you, that value is okay. So, and then walls, here are no acid walls, okay, no problems. And also you have the auction thermal, so you put here heat flux 0, so there is no heat flux at the walls, but if you want to add a heat flux, put it there, or you can also fix the temperature at the walls, or you have many options here for heat transfer. Okay, so let me go back to the material that I forgot to mention something. So as you select your water, remember that we have energy, and those properties can vary with temperature. So see that for density, you have different models. So remember we're talking in the equations about all the models. So let's use constant density, okay, for these values of temperature. I would say that density doesn't change much. And then also you have models for viscosity. So I think I introduced the Sutherland model. Okay, you have coefficients according to the property. So it's up to you, but let's keep everything constant. But here you can change. These are all your thermodynamics models. Okay, and scalar and transport, physical properties transport. Okay, so let me close here. And we have here, we went through this, boundary conditions were done. Here we don't need to set up anything, we are not normalizing values. Then we go to methods, okay? So probably you will have the couple method there, so you will have this, I choose default couple. So let's use the simple, okay? Let's play around. So select simple, okay, remember that we want second order accuracy for momentum, then turbulent variables can be upwind, leave it upwind, but if you want to go second order, it's up to you. And energy have to be also second order, okay? So this is a good discretization. And then we go to controls. So these are the famous, or let's say infamous, under-relaxation factor. Very important. Sometimes when you run and you see a steady simulation of that mysteriously crash at the beginning, it's likely probably that you will need to play around with this. So most of the time you need to reduce it. Sometimes you will need to increase. So see that you have here the industrial value, 0.3 for pressure, 0.7 for momentum, and then you have the others. Remember I told you I like to use 0.7 for all of them except pressure. So let's set up those. 0.7, 0.7, okay. And then we go to the defaults and we're going to see the difference. Okay, so we have everything 0.7. Then report definitions. I set up a couple of them. So I compute in the mass flow. Okay, so I compute in the mass flow in these three surfaces, and also I select this person. Person means that it will plot, it will show me the information or save the information for every single surface. If you deselect this one, it will be the summation of everything. Okay, it's up to you how you want to do it. Then I have the average temperature at the outlet. So this is interesting because I will use this average temperature because here I will have some oscillations as another criterion to control the convergence. Okay, so as you go there, select mass weighted average, field temperature, static temperature, and then outlet. Okay, put in the outlet and you plot that quantity. Okay, select plot. Okay, you will have the auction plot. You have many auctions there. It's mass weighted average. Okay, and then as usual, y plus value at the walls. Okay, after doing that, okay, be sure that you have all these three plots. Okay, so just to show you, for instance, to redo that one surface, I want mass weighted average. Okay, you select I want it in the outlet, I want temperature, static temperature, and I want it to plot, select plot there. Okay, if you want to save it to a text file, select there. Okay, do that. So we have these monitors, and then you go here, residuals, see that you have more equations, K, omega, and then you have energy. Usually energy needs to converge well, so you have this default. Okay, so these are the default values. Okay, and then see here that you will have this option, convergence condition. So besides these monitors here, you can also choose a value, okay, an integral quantity or whatever, to monitor convergence. Okay, so you can right click, create, and then let's create this one. So you activate it, give it a name. So I will call it condition 2. And what I want to do, I want to use temperature. Okay, and I want, for instance, it will start to iterate. So the first 20 iterations will be ignored. Then it will use 20 iterations to control this convergence condition, and the stock criterion will be this one. So for instance, this will be, if you put this one, will be 1%. Okay, so when you reach 1% of difference between iterations in this one, it will stop. Here we're using a small value. Okay, and then here you can also change the frequency, how it's computed. So here every single iteration. Okay, so you have your object there. Okay, and now nothing here. Initialization, let's initialize. So you have the option, standard initialization. Okay, you can put everything from steady condition, quiescent condition, nothing's moving. Okay, here you can put 30 and you initialize. Okay, or you can use the hybrid initialization. Okay, so that is quite good. I recommend to use hybrid initialization. So now that we have boundary conditions, initial conditions, all the models. So as you plot here, you will see that this one is giving you a good velocity field as initial condition. Okay, this is much better than starting from a 0, everything 0 at rest. So we have that, and what we need to do now is just to run. So here in conditions, remember enable, active, and print. Okay, so we'll print that on the screen so you have the reference. So let's run. Okay, calculate. I have 1,000 iterations there. You press calculate and off you go. So see that here we have the three mass flows at the surfaces, the average temperature, and see that it start uniform. This is the other, and then it's arriving the temperature there, the field is being convected. So remember, you see here this behavior, but this is an iterative marching, okay? So you are capturing oscillations, everything, but it is iterative, okay? It's not time accurate. We don't have time. So you want to have that time accuracy and see these oscillations, you will need to choose a Transient Solver, and you know those are tricky because you need to select time set and everything. Look at these residuals also, they're falling very nice. It's a monotonic way. Your Y plus, okay, we have a Y plus that probably is not ideal. I will show you a trick later. And see that we have this, okay, and see that the solution is telling you is converged, meaning that these residuals arrive to these residuals, but now it is monitoring the second condition, okay? So see here that it's telling you solution converged, but in terms of your residuals. Then it's checking the condition too, okay? It's checking for the difference here, okay, in this one. So we choose a relative low value. So this is what I was telling you, that sometimes it's very misleading looking at this one. So if we had to use this one, probably it will have converged, I would say, in about 180 iterations. Okay, well, we have the value here. It converges in 190. If we check here the temperature, you see that in 190 still the oscillations are a lot, okay? Probably might be 0.5 degrees, but you have the idea that it's still oscillating. So that is why do not rely in this here, okay? Just put some other quantities and start to monitor. Not necessarily you need to add these condition controls, okay? These can be also tricky to control, to understand how do they work, okay? Rename it. So if you don't want to use this, just deactivate it, okay? And then what you can do is just reduce the residuals, okay? So for instance, in this case, this one 10 minus 3, so let's put minus 4, okay? And calculate, okay? So that now we'll iterate until reaching that value, okay? Stop. And then you check your quantity. So see that now is a much better behavior there. Okay, so that's why I always monitor some other quantities, integral quantities. You have your mass flow, so what is going in is going out. So inlet 1, inlet 2, and then the summation is this one. Okay, so now that we have a solution, remember also reports. You have here fluxes, so also you can compute fluxes here. So see that you have the summation. So it's small values. You have heat transfer. You can compute the heat fluxes. Also, you can compute forces if you want. Okay, you have everything there, and you can compute also surface integrals. Okay, for instance, let's go surface integral, and I want the idea weighted average of watt of temperature in my whole domain. So you have that value. Okay, so I did some operation. Okay, it doesn't have any meaning for what we're doing, but get the idea. So you can do all this post-processing a posteriori as well. So now let's see some pretty colors. Okay, so you go here, click surface, and this is what we have. So velocity field, and see this, that here kind of we have a recirculation area, and here we have some other separation. Okay, and see the flow here, Then we can choose also temperatures to see how it's being transported. So enter here, there is a small diffusion, and then you have this, okay? Very nice. So this is 2D, we're going to do exactly the same setup, but in 3D, okay? And will be a little bit different, okay? But this is the idea, this is what we're doing. So you can play around here with all quantities. So let's look at the turbulence quantities. So see that here is where you have the fluctuations, okay? Remember this one is related to fluctuations. And we can also plot production of K. I can see where everything's produced and change your ranges there, okay, click to range, I don't want, and see that at the walls you have production, okay? And actually this case is using wall functions, okay? So for instance, if I let me go, probably we see that better with K. Let me go, okay, K, click, no, auto range. Okay, so change this one, let me go small. Okay, so see here, on this side here, see that at the wall is 0, okay? We don't have their fluctuation, but in this side here, see that at the wall actually is not 0. So all this part here is being modeled, okay? Here it's put in wall functions. You go closer here, you see that a small region here is resolving, and as you go here, everything here as well is resolved, okay? And here see that it's modeled as well. Here it has some separation, okay? So by looking at K, you can get an idea of the wall functions where they are enabled. Okay, so what else we can see? Okay, Eddy Viscosity. Okay, there is somebody that likes to see intensity, so you can look at the intensity. So see that here we have relative large value, okay? Intensity is about 22%. So there here you have the larger fluctuations, okay? But kind of for me, it's not very meaningful, okay? The intensity. Remember, intensity is the ratio between the root mean square and the average velocity, okay? So I rarely look at this value, but if you like to look at, you have it there. You will see where the areas where the turbulence model is kicking the most. So what else we can do here? So pretty much that's all, okay? We have done a lot so far. So now let me show you a trick, okay? So we have this. We know that our y plus is something about 22 in the area where we don't want. So how can we refine this mesh within Fluent? Okay, I don't want to go back to the mesh, but you can go and remember everything's parametric. So let me show you this trick, how to do it here. So you will see here that we're going to enter in advanced options. So this selection that I will do is valid for Fluent 19 and Fluent 2020, 2019, 2020 version. 2018, I don't recall, it should be somewhere in the ribbon, but here you see that you have cell register, okay? You select here, right click and choose new, and here you have many options. So I want to choose Y plus C. So basically I will put here a register, okay, or a monitor. It will get all these cells where I have a given value of Y plus, and then I can refine those cells. So as you press, okay, first you compute, it will give you the minimum maximum values. Okay, so you see that minimum allowed and maximum allowed. So those are okay, save display, and see that it's showing you the values, okay, where you have that condition. Okay, so as you play with this one, you will see that you will capture different things. So as you put here 1, I think it will be different. So you have also only these areas, okay? So play with these values, okay? So let's see that we capture here the whole boundary layer, okay? So we have that register, okay? And here you see Y plus star. So what we do next is, now this is, you can access this in the ribbon. You go into domain and you have the option here, refine coarse. So what you do, refinement criteria. So we select a group of cells. Also you can do coarsening, so you can do another selection. For here none, we are not selecting anything. And now you can select, there are different options here, but defaults that you have here is okay. So here, see that you have maximum refinement levels 2. So you choose your refinement level. So I would put here, let's say 4. You go at that display. Okay, you don't see it, but here you see that you already have the message here that you adapted. Okay, see that you increase the mesh. Cancel there, and let me now let us visualize the new mesh. Okay, you have it here, display, and see that you have the refinement there. Okay, all the mesh. Another option to do refinement, you go back here, you have many options. Okay, so for instance, let me go and I will fill variable. Okay, so let me choose temperature. Okay, we know that we have some temperature, nice temperature distribution. And I want here cells in range, compute, show me the values. And I want to do it, let's say 50 from 30. Save this place and see that it's tagging all these cells where these values are contained. Okay, so now you can add another refinement here. Okay, so you have it available. So there is another one, let's say boundary. You can choose a boundary, all the walls, okay, and also the cells growing, and see that shows all these cells. And now, or you can go 3 or 4, I see 4 cells from the wall. You have that registered there, and again you can go here and add refinement. Okay, so you can go boundary, just put 2, okay, at that display. Okay, then you see, and you can do it also for the field value of that display. Okay, we have there. So now we can visualize the mesh and see the new mesh. Okay, so this works with any type of cells. Okay, you have triangle, polyhedra, you can do the refinement. I don't recall this polyhedra works. Okay, I need to check, but triangles and quad, the most general ones. Okay, so see that you can do this refinement posteriori as well. Okay, you choose your criteria, you have gradients, many things implemented. And let's run this simulation. So we don't need to restart, just get from the previous solution, go run calculate, and for instance calculate. Okay, and see the results have a jump. Okay, you have a new mesh, you interpolate solutions, and we'll start to iterate. So maybe it will be slower, likely probably slower, no different mesh. Okay, and let's see what happens. So this one will be, it might be difficult to converge. I think in one point the results, they might get stalled there. But the fact that the residuals also get stalled there, it doesn't mean that the solution is wrong or it's not converging. We saw that previously, with the previous tutorial, that it might be an indication that you have it unsteadiness. And see that we have a much nicer mesh. So probably this mesh is capturing small scales that this steady solver is seeing, but it doesn't manage to get to your residual because you have that strong unsteadiness. So it might be better to go to an unsteady solvers. And actually I see that behavior here. Okay, so at this point you monitor some other quantities, see that now our y plus average is about 6, and see that this quantity is not oscillating anymore. So we can say that this is safe to stop. So see that this one is not telling anything. Okay, this one is the one that is telling you if it is okay. Okay, it's not oscillating, or the oscillations are small and your mass flows are okay. So let's stop here, and we can go and visualize our solution. Display. Okay, let me go to velocity. So see that we have solution velocity. We go to temperature there. For those that are doubt that this is not the mesh, see that this is the actual mesh. Refine it. So interpolated the solution, hide it. Okay, and for instance we can check, okay, pressure. We haven't seen pressure, so see that you have your pressure field, and you can see here I immediately see that here I have the shedding, and this is why it's not converging. So you have this low pressure. Remember that this is a vortex, and this is a vortex here that is shedding, and this is what is getting installed. So maybe we can see that vortex better as we plot vorticity. We change the range, put okay, too low. So see here. So here you have fluctuations here, but here see that you have this fluctuation. See that? So this is the problem, that now in this case, this is what is keeping the residuals stalled. Okay, so it might be a better idea to change to, I don't know, a steady solver. And then we can go and plot vectors. So we have velocity vectors, and let's see what's happening here. Okay, so see that actually we have the recirculation area, what I was telling you, flow separation. Okay, so we go here and see that you have the flow separation. Okay, and then also here you have another flow separation. Okay, and what else? And let me put, and now also, okay, we go here, turbulence, and see that if I plot this value of k, see that now k, remember previously k was, everything here was red. Now it means that it was using wall functions. Look at now, it is resolving there. So let me reduce, so from 0.1. See here, you go close. Now this is resolving. Okay, the previous one everything was red. And sometimes it's better to see, instead of this one, is the production of k. So outer range, and let's see, should be something about that value. Okay, 5,000. Okay, you have it there. Dun, 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 dun. Okay, here, see that it's produced here, most of the turbulence produced there. Then also you have dissipation rate. Okay, outer range. So one thing also that we're looking at these quantities now. Usually as well, you don't pay attention. You follow good standard practices. You need to do this, but we're working in turbulence, so we're paying attention to all these quantities. Okay, see that everything is dissipated at the walls. Okay, so they're probably for the smallest scales. Here you have the model that is kicking in. So all this dissipation is the model, like it probably is the model that's doing that. Okay, so what else we can visualize? So let me go here, velocity. Okay, we have everything there. So I think we have done all these options. So I show you some advanced post-processing, and let me close here. Use settings for current. Okay, I don't want to save those settings. And now you see here that you can keep computing. Okay, so let me do some cleaning here, housekeeping. I don't want that. And let me show you also, you can do the post-processing using CFD pause. Okay, I don't like CFD pause, but well, okay, let's take a look what you can do. Okay, it's a little bit tricky to use. Okay, so if you use previously CFX, CFD pause is the post processor for CFX. Okay, so basically the default should be something like this, very clean. Okay, so okay, let me erase this one. I don't like this one. So right click, you can erase those entities. So here you can select, so you see that it's fully three-dimensional. Okay, so you can select faces where you want to do the plotting. So if you select symmetry plane, double click, see that here you can plot variables. So first visualize, and then you choose your variable that you want to plot. Okay, then press apply, and you have it there. Okay, you can add also planes. Okay, so this is a 2D case, but if you want to visualize in a cog plane, here you have all the options. Okay, cut plane sizes or faces. Okay, probably when we go 3D, we're going to see that. So here, for instance, I already add a line here. Okay, so I don't recall. Okay, and we can do some sampling there. So also I think I have a chart, but let me do it again. So you can select this line or here chart. So it's like the XY plot in Fluent. So here you have, even here the advantage here that you have time series. Okay, you can do the sampling and changing in time. And x-axis, you choose your variables. I want in y-axis. So here, let's say I want this one, and this one I want, let's say, velocity. You choose whatever you have. Apply. Okay, it's missing something. Okay, the location. Okay, you go here, data series, location, where you want to do the sampling. Apply. And there you have it. Okay, so you choose your variable here. Also remember where you want to apply that sampling. So you can have many samplings here. You can add more. And also interesting here, you have variables. You have many more variables. So you have a calculator here. Okay, so expression, you can compute new expressions. Always right click new and give it a name. Okay, and then you put your definition. So here you need to go to the user guide to know the definitions, but right click and you have expressions, functions, okay, cell, CFD, so you can compute everything there. Okay, so reset. Okay, then calculators, more sense. So yeah, it's relatively easy to use, but honestly, I don't use it very often. I don't like it. For instance, you can also have streamlines. Okay, so I want to release streamlines from the inlet or from this line. You can go here, streamlines, particle track. No, it's not particle track. Okay, particle track is something else. Streamlines here, streamlines 2. And you choose all domain, start from, you choose this for phase, line 1 in this case, apply, and then you have your streamlines. So you can add the streamlines also here in the bottom. So you go now, new streamlines, from where will be inlet 2, apply, and then you can change the colors, everything. Okay, release for a point. So here you have planes, point, group of points, so you can release streamlines there. So play with this one. You have an I think the material that you download with the academic version, you have a nice access to a nice tutorial for this. So I will close that one there. So the final thing that I want to show you here, I have another solution that I run here that I put some advanced sampling features. So basically it's pretty much the same here, but here I was computing the y plus normal to a wall, all those quantities to do some plotting. Just to show you that can be done also in Fluent. It's trickier, so it's better to export the data and then use MATLAB or Python, whatever you use to do that, to plot now the normalized velocity and much more now. Okay, so we have the same solution. I don't recall what if I added. Okay, probably I added some refinement there. But look at the new thing that I have here that I added here is custom fields. Okay, oh, I don't have the custom fields. I didn't save it. But okay, just to show you. So what I did here is that I added this line. Okay, so see that. Okay, static pressure, no pressure, and I can do the sampling in that line now. And okay, graphic will be here. Okay, so I have a line here, this white line. So you can plot your velocity profile, everything there, and you can plot now your y plus and everything. So the idea is that you can compute those quantities here. Okay, so you go in cell, custom field function, and here you have this calculator. So for instance, you want to compute shear velocity, u tau. You go here, and if I will recall, it will be something like shear velocity. So let me go divided density. It will be Okay, the wall shear stresses divided density. Do you have access there? Select, close, and here is 0.5. Okay, so you can define, and you have that constant field there, and then you can plot it. Okay, so save displays. You have here custom field, and you have your shear velocity. Okay, then you can go and compute y plus. Okay, u plus in the same way. Probably the only tricky one will be the y plus. Okay, that you need the distant normal to this point. Okay, so here I compute the value of shear stress that I put there. I think correspond to the line that I have here. But also here you need to have the normal distance from this wall. You will need to add another custom field object. You go here, new, and you will say that that one will be new. So that one will be mesh. It will be x coordinate, this one. So that, and it will be c minus 0.4. Define, and as you go here. Okay, see that now it's 0 and it's growing. So as you plot that line here, okay, we don't see the line drop mesh. See that now we have the coordinates starting from 0 to here. So we have, you can compute shear velocity, you have your velocity profile there, and you have your normal distance, and you can you can do all the operations and get your profile. So for instance, you go here, and let's see the velocity profile there. So I don't want this one, and I want that line. A new custom field will be 1. And there the velocity. Okay, and I want it here. Okay, so you should have this one. Well, okay, probably okay. This one is the final solution. Okay, this is the initial condition. I need actually run the simulation. Okay, but this is the idea. Okay, you can add all these custom field objects here to compute those quantities and then plot the profile there. But okay, this one, I think the Fluent needs to improve these custom field objects a little bit. It can be tricky to do it. So I think that is all that I wanted to show you. And the next case will be the 3D one, exactly the same, but the 3D. Okay. Okay. Sorry. Let's continue. I forgot to show the difference when changing the under-relaxation factors. Okay, so let's run another case fast. So I launch again. Okay, so okay, now I open the mesh, the one that I refined, and so as you see, I chose the solution. And let me close that one. As you refine your mesh, you will be opening this case refine. I don't want to open. I want to go to the original case, which is safe in setup. Okay, so go there. So here you have everything there, the original setup, everything safe there. So read the boundary conditions, everything is defined, but just initialize and let's run with different under relaxation factors. Okay, so we have the case. So let's go, for instance, okay, we have always the simple, we have these values, and let's go default. Press here, and these are the default values. Initialize. Okay, and here enable the monitor, I think, convergence monitor. Okay, it is enabled. And let's see today. So as you recall the previous case, you will see that you will see the difference already. You will see the difference here in temperature. See that it is very fast. Okay, it's going to this value, stabilizing about that value in the outlet. So remember, previously was here, and then it went up So you see, by using different under-relaxation, we're advancing the solution faster. Okay, so this one, you see that the monitor that we added is already converged, but now it's this solution that hasn't converged yet. So see that it's telling you, okay, your monitor converged, that is okay. Now you need to fulfill this condition. So in this case, the larger and the default Fluent under relaxation will give you a faster convergence rate, and the solution is pretty much the same. But let's go, and let me go here and put every 0.9, increase all this under relaxation, okay? 0.9, 0.9, 0.9. Okay, let's see what happened. So this is telling you that it would be much faster. However, you are giving out some stability to your solution. So let's see if that is true. Okay, what happens? So see that now it's divergent. So if you want to see Fluent divergent, that some people say that Fluent never diverge, you have it there. Okay. So again, okay, go back here, put default values. So remember, this one is very important. So most of the time, I like to change this value to my personal value, to my personal preferences, but it's up to you. Okay, you need to do the experiment. This is a nice case that you can play with many methods. And let's use another method. For instance, we have the simple C. Okay, simple C is more robust than the simple, but the default values that Fluent is giving also, there are no ideals. Remember from the theory that simple C, you can use larger values for pressure. You can go to 0.7. So sometimes happens that the simple C with these values, they diverge. Okay, so let's see what happened in this case. I haven't run it. Calculate. It might, okay, probably will have a very slow convergence rate. I already see that this is slow, the convergence rate. Okay, it's going nice. Okay, now it's going nicely. But see, different methods, different convergence rates. So here, already converged this monitor. Okay, it's telling you, but this one now is waiting for this one to converge. So let's see, should converge soon here. Okay, this one, voila, converge. Okay, what is energy thing is the one now. Okay, I know. Okay, converge. So it converges about 200. Okay, let's say 203. So now let's rerun here and let's increase this value. So here we can go 0.7. Okay, the others are okay. Initialize and compute. Off you go. So let's see. So usually pressure will affect continuity. Okay. So we'll see a faster convergence rate there. So see that this one already converged, it's telling you, and now here this is one that is missing. So energy equations, I think is already converged. Yeah, pretty much all values or variables but continuity. So now it's continuity going down. Let's see. And voila, in 173, okay? So you see that this is kind of a way to controlling the time state, that fictitious time step. And for instance, on something that we haven't done, let's go 0.1, 0.1, reduce everything. So this one will give you the most stability, but it's painful slow. Okay. And 0.1. Okay, now initialize. Calculate. And off you go. Okay. So sometimes maybe when you have really strong, let's call stiff physics, it is a good idea to use low values at the beginning. For instance, shock wave or chemical reaction, stuff like that, combustion. You use low values at the beginning, probably like for 100 iterations, and then you stop and start to increase those values slowly. Okay, so see here that it's telling me that this quantity, see that it's telling you it converts, but see that it's not the actual value. So now see that it's very misleading, because the rate of change is really slow, so this quantity is not changing. The flow, the temperature hasn't been convected to the outlet. See that it's still 24. Nevertheless, it's telling you that has been converged, and this is moving very slow. Okay, so this is the problem when you go too low with those values. So let's see what we have there, actually. See that the temperature is evolving, it's moving slowly. So if I put T, see that T is entering there. So this is the effect of changing the under-relaxation. So let's go here, default, to do the last exercise, default here, okay? And I want just to show you, we have seen how it converges, we know we have an idea of the solution. So let's go to viscous and put it laminar, okay? DNAs in theory. So let's see what happens here. So you go again, initialize, and let's go. Boom. Canon, utilization. Okay, it's telling me probably Y plus. Okay. So yeah, Y plus is not. Yes, type there is you give it. If it gives you that error, type there yes in the TUI, because it's telling you that basically you need to deactivate Y plus because it's not computing with the laminar solution. So type there yes will be deactivated. Okay, so in my case, okay, 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 so it has been deactivated. Let me initialize again. Come on, no, not again. Yes, stop. Okay, before doing anything, let's go here and plot, and you deactivate it, okay? Deactivate, initialize. Okay, now it's running. So we're using the couple solver, that is the most robust one for steady solutions. I already see that it's having problems. Okay, bam, 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 bam. So see that it's oscillating, it is stalled. Then let's see, it might go down. Okay, but this behavior is already telling me that there is something going on there. So if I stop it here, and let's see the solution. We know that we have a separation zone strong. Okay, so let me plot velocity. See here, okay, and see here the separation also. Previously it was smaller. See here how you have this strong recirculation. Okay, and if we keep computing, this will if you start to size your solution, you will see here an animation. Okay, you will see here how this vortex is evolving and just iterate the interacting some structures there, but it's not time accurate. Okay, so the advantage here is that we can have fast outcome, but yeah, this is already, I know that this is an indication of unsteadiness. Okay, so if I go again, let me plot contours and see that we have that unsteadiness there. So if we go here and we enable any models we want, and we go here, calculate, we don't need to initialize, we just take this field and we go and compute. See that now this is the stabilizing factor. See that now it's iterating, converging very smoothly. So again, don't be misled by these under-relaxation factors. When you see then stalled, means that it's likely probably that you have a strong unsteadiness, so it probably is better to change to an unsteady solver, or probably it's something with the physics. So you are missing your turbulence model is not right, or something else. Okay, so check also your physics, and as we check the solution, we have there here, so see that this recirculation and there attachment. So that was all for this 2D tutorial. So the next one will be the one in 3D, pretty much the same. Okay, so just play around with this one with the under-relaxation factors and get your feeling. Very easy to use case, and try to plot your y plus here at the wall. Okay, the normalized velocity, so using the custom field functions. Okay, well, that was all. See you next time. Bye.